introduction. I'm Brad Gesselin with VIAVI Solutions, together with my wingman panelist, Roy Anderson. We both specialize in supporting our CellAdvisor product lines. Today's presentation is about interference hunting. The topic of interference can be very broad, and I understand that there can be a very diverse variety of sources, but I'm going to try to share with you today a perspective that I have as a test engineer. And in fact, much of what I have as far as material also came from Roy Anderson, so you're in good hands. Basically, as a test engineer, I see there's two phases to basically test. There's detection phase, where you're looking for functional performance problems, and then the isolation phase. Right here, I basically ask the question from the methods below, how do you actually go about detecting interference? You know, is it end-user experience, is analysis of OSS systems using example OCNS AIRG test modes. These are, in fact, test modes that are able to push your transmitters to full power. Built-in network equipment manufacturers' alarms. A lot of times I hear that people are basically chasing down that they've got an alarm from their equipment manufacturer, diversity alarms, whatever the case may be, and they're trying to otherwise now isolate it. Otherwise, there's spectrum analyzers and signal analysis that you can use to otherwise detect to see that you may otherwise have problems with your network. But again, noting that all these items above are susceptible to good, varied, and bad test setups. Effectively, what I come to as far as a conclusion of my experience, to efficiently detect 100% of interference, really ideally you should be using all the above. And again, as far as fault detection, in an ideal world, you'd like to have 100% fault coverage to know that you know exactly where all your strengths and all your weaknesses are at. The next slide comes from my experience with the military. I came to appreciate in a lot of the contractual requirements that we have or were issued is that interference was a big concern. But there's in fact only 4 basic components of interference. You have emitters, which are at the top, and emitters can be either conducted or radiated emitters. And then you have susceptibility. And again, equipment can be susceptible to conducted or radiated susceptibility. So in terms of interference and identification, oftentimes you're looking to identify, okay, where's the problem? Is it an emitter or is it a susceptibility issue? But the bottom line, as far as identification, one should realize that of all these different emitters, you can have RF electronic devices, power supplies, projectors, laptops. All of these things can actually emit interference. Electrical devices, the environment, example, lightning and static. These too can interfere with the RF conditions. You can also have physical objects that can actually interfere with conducted information, or when you're over the air and you're part of radiated emissions and susceptibility, dust, fog, there's a variety of items that can otherwise interfere with the quality of signals. But as you can see here in really large, bold text, the highest probable cause of RF interference starts at the cell site. And the reason for that is that the cell site is where there's a lot of items as far as usual suspects. You have to consider the number and proximity of high power sources right there at the site. The components and or insulation can affect TIM, harmonics, spurious emissions, leakage, arcing, grounding, signal quality. All these items can otherwise actually, your highest possible, suspects generally are right there at the site. That's not to say that external interference can't be prevalent, but in most cases in my travels, oftentimes the folks that are trying to find the problem may be looking around the cell site, not realizing the cell site itself is causing the problem. Other areas that I've seen quite common is in 3G and 4G technologies, they're using poor coverage designs. Reality is this is a frequency reuse of 1, and you have to understand that your ideal goal is to minimize overlap between adjacent sites and sectors. Another item which is a very common source of problems, tower versus roof sites. On a tower you get a nice triangular shape, and all your antennas are shoulder to shoulder, and they generally don't have too much problem with each other. As soon as you go to a roof site, which you're looking at a rectangular shape, and you're otherwise trying to create a cellular pattern, which is oftentimes a 6-sided hexagon, you sometimes have antennas pointing at the backs of other antennas. and these can be clearly sources of interference. I've seen issues where they'll want to put the low frequency or the high frequency on the left or the right because the patterns and the frequencies otherwise cause more problems with the spacing that they're dealing with those antennas on that roof. But otherwise, when you say most interference, because a lot of spectrum clearing has been taking place within our industry, most of your external interference is oftentimes close to the site. The bar or the pie chart I show on the bottom is just one example of a market that basically provided us kind of their perspective on examples of PIM. And you can clearly see that the bulk of problems that they have otherwise found has been simply with the installation. Loose, dirty, bad connectors, jumpers, even surge arresters and passive devices. At a much smaller scale, antennas, yes, they can be, when you say sources of PIM, azimuth, meaning where that antenna is pointing at, and then outside interference. Again, their experience has been that in their market they had very little outside interference. Most of the problems were in fact self-inflicted. This slide is trying to share as far as detect, identify, and locate. One of the single best ways that I have seen detection of PIM is actually using the reports back from the network equipment manufacturers, because virtually every one of them has reporting on the resource blocks. Over time, we can otherwise witness or see what type of amplitude you're seeing on the uplink at various times across all those various resource blocks. And as far as initial detection, I highly encourage that be one of the best ways as far as monitoring and looking for PIM across your cell sites. Here you can see examples of, this is normal traffic on the left. Here in the center, we're actually looking at a CIPRI interface. In fact, all of these displays are in fact taken from CIPRI. You'll notice the mode in the upper left-hand corner. So this was actually taken from a piece of fiber. Here in the middle, they switched between two antenna containers, and you can clearly see that the second antenna receive path is clearly being affected by PIM because of that sloping characteristic that is quite prevalent within this display. This next slide is actually kind of a bit of a marketing to share with you that we have other products, obviously. This is taken from our RANadvisor True Sight. It's an Android-based application that runs on the handsets. But one of the features that's been recently added is a path loss imbalance magnitude. So as one can otherwise expect on both the uplink and downlink, the path loss, or the physical space that signal is traveling across, you should have the same amount of loss and RF conditions for both uplink and downlink. If you do in fact have interference, oftentimes one of the quickest ways to see it is on your handsets to see that you actually have a path imbalance between the uplink and the downlink on your network. This slide is to, once you know that you have a PIM issue or some type of a problem that may be local to your site, oftentimes I see people, even with a PIM tester, they'll recommend basically a tap and torque, meaning that you basically go around and tap on coaxial cables, and if you have connectors available that you can give it a little extra torque with a torque wrench, make sure it's at the proper pounds per square inch. These are excellent ways to otherwise, let me say, determine whether or not you've actually found or isolated the source. Now, oftentimes the problem, though, if you have fiber to the antenna up on top of the tower, these are not readily accessible. So one of the things I actually highly encourage and when you're visiting a site and you're dealing with PIM is to have the ability to invoke, example for Ericsson, they refer to it, and 4G LTE technology is AILG, Air Interface Load Generation. OCNS is the other term, and it actually originated with 3G technologies. But both of these are examples of taking your transmitter and placing them into test modes where they're basically allowed, or you have settings that allow you to push the transmitters to full power. And ideally, if you're monitoring your receives at that same time and you see a correlation where your receive levels increase, you can clearly determine that you're in fact interference or dealing with interference that's otherwise self-inflicted. But some of the other ways to isolate PIM is by dissection, meaning you actually have to, take off the weatherproofing tape or whatever's covering it up. Inspection, doing visual inspection of the actual RF components, or even, as you can see on the far left-hand side, putting a PIM-rated load at key locations. Example, where an antenna is at, if you're able to replace that with a PIM-rated load, and your problem, your passive intermod, goes away and you don't see that interference anymore, then you conclude that the interference is in fact either the antenna itself or something actually in front of the antenna. But as I also make reference to and/or RTP, DTP, range to PIM, distance to PIM, I still have to admire that with PIM testers, especially if you have a very long coax run with a variety of components, range to PIM, distance to PIM still definitely has its value. But as far as detection, I don't have the same, ambition to use a PIM tester to detect PIM because there's far, lower cost and more efficient ways of doing it, and also less disruptive because you don't actually have to open up any coax circuits to otherwise determine that you in fact have a problem. So I do admire the piece of equipment and what they perform, but I also understand there's a time and place which I would ideally use them. But I also want to make sure that you clearly understand fiber, and especially dirty fiber, can be a clear source of conducted interference, meaning that you've got something that's going to interfere with the RF coming over the fiber. And I really like the expression fiber hygiene. I know most of the customers that I call upon that have talked about their contractors, this is not, these are guys that are basically staying out late and, partying a lot, and they're people who otherwise get off on, they still like climbing towers. And my apologies if I insult anybody on the other line if you're a former tower climber, but I still suspect you understand what I'm talking about. But more importantly is finding a term, and I really like this fiber hygiene, to basically imply, I don't care if you bathe or not, but when it comes to my fiber, my RF connections, I'm looking for very clean, very pristine conditions because I'm looking to have an optimal high-performance network. And I don't want to deal with interference from dirty fiber. So ultimately what it comes down to as far as your best insurance to prevent interference is to know your setup quality and the coverage that it was intended to cover within your network. So that means clean and tight wires and fibers, clear dynamic range between idle and full power. When I basically make reference to that, I'm oftentimes thinking in terms of DAS systems and also my test equipment because to fully understand or to make measurements, you may have heard me make reference to functional failures and performance failures. Functional are easy. Did you turn it on? Did you swap a cable? These are the easy things functionally that you can oftentimes isolate what is the root cause. But in performance problems, you have to understand dynamic range. Dynamic range is that area that's most linear. You can have something that's off or a noise floor, and you can have something that's fully on or saturated, which is creating thermal noise. And understanding where you're at on that dynamic range, this applies not only to DAS systems, but even test equipment. And test equipment has, and this is part of that, a quality setup, understanding where you're at on that scale so that you're not overdriving or underdriving anything. But otherwise, the other thing as far as know your setup quality and coverage, minimize coverage overlap in areas of dense usage. This comes back to also self-inflicted interference because frequency reuses of one, the intent or the goal to get the highest capacity and throughput is to minimize the overlap between sites and sectors. Now, as always, it never hurts for these presentations to constantly remind people that we're going to be talking about units of power generally in dBm or dB, which is actually the ratio or sometimes the differences in dBm values. And to understand that similar in mathematics where you have addition, subtraction, multiplication, division, things are becoming, faster and furious. The logarithmic dB scale is effectively the next level in mathematics where you actually become into multiplications of either or divisions of times 10, divide by 10, times 2, divide by 2, 25% change. These are all parts of that dB scale and very, very important in understanding how you're otherwise finding interference. But I have to be honest with you, and again, my thanks goes out to Roy Anderson. I've seen this equation countless number of times in my 30-year career, and I kind of got it, but I'll be honest with you. It was when I saw this slide that I had one of those aha moments of, oh crap, I should have paid closer attention. But I started to dissect this a little bit further. Now, this Boltzmann's constant, I have no desire to try to memorize this value, but bottom line is it's constant. It doesn't change, so I don't really need to memorize that. This next variable in the equation is temperature in Kelvin. I don't know if too many people use the Kelvin scale, but I can clearly see here that 273 plus the temperature in centigrade, only results in a 293 value at room temperature, and I know from Fahrenheit to centigrade that centigrade is a compressed scale. Well, let me share with you my experience that I actually went through this equation and started at room temperature and did plus or minus 50 degrees Fahrenheit. The change in the dB value of plus or minus 50 degrees Fahrenheit was less than plus or minus 1 dB in change as far as power levels. For all intent and purposes, I can pretty much think of this temperature also as almost nearly a constant. It doesn't have nearly the effect on the outcome of this equation as does bandwidth. And here's where the magic begins. I actually have a customer who has a personal vehicle that on his license plate he has 174 dBc. And anybody that sees those license plates that understands RF immediately understands his reference and knows that this person is very efficient and understanding of exactly power and noise. Because at 1 hertz, this is the theoretical reference or starting point, neg 174 dBm. So simply if you recognize and remember this one value, and knowing the dB scale, if I double the bandwidth, 1 hertz to 2 hertz, that is twice the area. That's 2 dB, or I'm sorry, 3 dB, because you've doubled the amount of area that you're measuring. So you're at neg 171. So what this table further shows is that as you move through different bandwidths that are oftentimes relative to the different technologies, these in fact become the theoretical starting point for how much power you can otherwise measure. If you ever use a piece of test equipment and they measure below this, you immediately know there's something wrong. Because in fact, these are theoretical. You cannot get any lower than this. Now, you will have values, and you'll see in some of our slides that you actually have to add a little bit more to this because there's always a noise figure, which oftentimes is part of the system. But needless to say, this is probably one of the single most important slides of otherwise understanding and finding interference by understanding exactly where your noise floor is at using Boltzmann's constants, or that KTB equation. So this next slide, as far as detecting interference, this is really getting to the, when I say, one of the root analogies I like to use. God's gift gave you eyes and ears for sound and light. And most of us, throughout our entire waking day, we take for granted what we see and what we hear and all the details that we otherwise are able to gain from that. When it comes to detecting interference, your single best eyes and ears for RF is, in fact, a spectrum analyzer. But in order to use it efficiently, you have to know how to use it, because there are a number of settings that can otherwise impact what you see and why you're seeing what's on the display. It starts out with, remember I talked about dynamic range, and an instrument has a dynamic range that can be extended. This is courtesy of these first two items, the attenuation and the preamp. The attenuation is going to be used for very strong signals. Example, if you're using a hardwired test point on receive, you oftentimes, or transit, you oftentimes have attenuation that you need to apply, otherwise you're overdriving the instrument. For very weak signals, example with over the air and using an antenna, you're going to want to use the preamp to extend the dynamic range into that low part of the signal strength. Min and max traces. As you're adjusting resolution bandwidth there at the bottom, and depending upon your span, there's no way that anybody that I know of is going to memorize every single trace that goes across that display, especially when they're updating it, at 20 milliseconds. Every time 20 milliseconds you get a new trace. So one of the single best ways of seeing whether or not you have a problem is to turn on additional traces on your spectrum analyzer. Example, using min and max hold traces. And they will clearly share or display that you have issues. But otherwise, the frequency span resolution bandwidth, as you can see in this illustration here, as you start out with a very wide resolution bandwidth, you tend to get very high power levels. That corresponds to that KTB equation. As you go to very low resolution bandwidth, you start seeing more of the details. But you can also see that you start seeing on this trace lower and smaller values. And you can also see here, from example, where the preamp was off with 10 dB of attenuation, this is effectively how a spectrum analyzer works. But again, if I was using these settings, I'd probably be expecting to look at a much stronger signal. But when I'm looking at weaker signals, I generally want to have 0 dB of attenuation, and I want to turn on that preamp. This slide is actually showing clear examples. In fact, on our instrument, you'll notice in the lower left-hand corner, that letter C. This stands for captured trace, meaning that whoever did the screen capture, actually, this was not a live display at the time that they captured it, because both of these traces were, in fact, already captured and static. But what they did was they actually captured the one trace using a resolution bandwidth of 300 kilohertz with no interference. Then they, after they captured it and made it static, they dropped the resolution bandwidth to 10 kilohertz, and here they can actually see the interferences being detected on the edge of that signal. And I can actually share with you, I've been very, very, very uncomfortable over the years as I've watched and witnessed many markets who have deployed UMTS and they've had GSM not only on the edges, but oftentimes, in fact, you can see it right here, they'll place GSM signals right in between two UMTS carriers. Now, for me, that kind of is out of my comfort range, meaning that I don't want to be encroaching too close onto other technologies. It's not to say you can't do it, and it's not to say that impact may be minimal, but I can give you one example where they're deploying a DAS system that they decided to omit GSM coverage in that DAS. And this adjacent signal became a major problem because a lot of the people that were inside the assembly hall at the time had actually switched their phones to GSM-only mode, which meant that literally their phones were screaming to try to get out of the building to a GSM macro site. Meanwhile, because these GSM channels were adjacent to LTE and UMTS, this strong transmit power on the uplink was actually interfering and preventing their other technologies from reaching their optimal performance. So be careful when you're otherwise placing carriers next to each other, but also recognize in terms of settings, you can clearly start seeing more details as you start lowering resolution bandwidth. Here, as far as detecting interference measurement techniques, again, the max hold, min hold. As I talked about that before, here you can clearly see with a max hold, that there's a signal here, which is GSM. As you do a min hold, really I don't see anything that's persistent in way of interference except for this trace that otherwise shows a WCDMA, meaning that even on a min hold, the WCDMA always has some type of a presence at a very low signal strength, where the GSM seems to at least at sometimes go quiet. But the times when it's actually transmitting, you can see quite clearly that, yes, the signal as max hold shows that it actually, in that test point, shows a very broad amount of energy. And as I look at this with a span of 3.6 megahertz, that means that each one of these squares going horizontally means that each one of those is 360 kilohertz. So given that this is about 200 kilohertz wide, that's about right. Whereas, yeah, there's some, there's clear light. Here again, get back to this legend. Notice the uppercase M on the yellow trace. That's a max hold trace. The orange is a W. This stands for clear right, meaning that orange line is constantly changing. So whenever they did the screen capture, it just so happened that that's what the spectrum looked like at that particular moment. Notice the white trace is a lowercase m. This is, in fact, the min hold trace. And again, we don't see any problems relative to the min hold trace on this display. Now, at times, you're also going to have to deal with time division duplex, which means that your uplink and your downlink are sharing the same spectrum. So in terms of detecting interference, you definitely have to use a gated sweep. That's one of the methods or techniques that the instrument does support, and I believe that at some time in the future We'll probably have another webinar that will be going into more of the specifics of how to set that up. But here we're actually showing where you can see where the TDD downlink is. Here's where it's basically transmitting. Here's during the uplink. And we can see that within that same part of the spectrum that in fact there is some TDD uplink interference that can be seen when you're not transmitting. So being able to use the spectrum analyzer with the gated sweep more clearly helps to illustrate that yes, you do have some spectrum issues in that spectrum that would most likely affect your uplink. Not very likely it's going to affect your downlink, but uplink is definitely going to be affected. Now, in terms of identifying interference, one of the areas that I frequently want to make sure that you otherwise understand is that your own signals and performing signal analysis. That's one of the greatest benefits of the CellAdvisor, the base station analyzer, the 785Bs that many of you have, is to actually look at the signal and the quality of that signal itself. Now, you can do a variety of signal analysis, whether it be spectrum analysis or looking at constellations, looking at traffic, looking at air vector magnitude. There's a lot of variations that can otherwise help you to identify whether or not you have sites or who is trespassing. If you see a technology in an area that doesn't belong, you can use signal analysis to otherwise get the identity of that technology, so that when you call up to the, when you say suspected service provider that's actually causing that interference, and you start sharing with them details, it's hard for them to ignore that you've in fact uncovered where they're trespassing on your spectrum. So signal analysis can go a long way to that identification. Getting back to that bandwidth, as far as when you're doing spectrum analysis, you should be able to understand, or the person that gave you information, they need to tell you what time period and what frequency was being used when they're discussing power. Because some of that KTB equation, where the bandwidth is a single variable that has the greatest impact, you basically need to understand where is their reference coming from. But also recognize this, within a spectrum analyzer, before that first line trace gets shown, there's actually a variety of samples that are taking place even before that line trace gets presented. So recognize that in your setup of your instrument for your trace display, you will find that there are settings that can default to RMS values, which says, okay, we're going to do the root mean square on all these values, so we're just going to show you a very clear presentation of spectrum. But many of the veteran people out there that I've met that have done interference hunting is that their single greatest asset is to actually change that setting to peak power. The reason why is that if they do have an interferer out there that may be intermittent, they don't want that signal strength averaged into all the other samples that were taken. They actually want to collect all the peaks. Because when you collect all those peaks, oftentimes the signature becomes much more prevalent or obvious that, yes, there is a problem within the spectrum because you didn't average it in with all the other signal strengths within that same part of the spectrum. So things can vary with wider bandwidth, but the bottom thing is that be sure, in bold, you understand the time and frequency implications of the value you provide. If you don't understand the bandwidth of the power value, the DVM value, that number is meaningless. So you really need to be able to communicate well when you're talking about a power level, what is the bandwidth in which you're talking about it. So this gets back to that KTB equation that we talked about earlier. The noise power present in common communication channels. Notice LTE, that's approximately 180 kilohertz bandwidth, very similar to GSM, 200 kilohertz bandwidth. Their KTB starting point is a neg 121. Now notice that there's a little asterisk right here because it's the only technology shown in this slide that doesn't have a frequency, it has actually a frequency use greater than 1. Meaning that in GSM, as long as you have large separation between channel usage, between sites, not a problem. You can reuse GSM channels. But one of the key things to understand with LTE, CDMA, EVDO, and UMTS is that all three of these technologies, or four if you count CDMA, EVDO twice, is that they're all a frequency reuse of 1. So they're trying to share the spectrum. And you can see what the starting points are, but notice also that to try to understand ballpark-wise where you should be, adding 3 dB of noise from the radio's antenna, the cable, and receiver, oftentimes it's referred to as the first electronic circuit that it runs into that otherwise determines what is that noise figure. So oftentimes adding 3 dB of noise to the radios puts you closer to where I would expect, your spectrum analyzer display to be. But again, it also comes back to the quality of your spectrum analyzer. Oftentimes with the 785B, I've seen noise figures about 5, 6 dB. The official name that's used to describe it is DANL, and we'll talk about that more in some of the next slides. This slide is to otherwise relate to radiated susceptibility, and back to that frequency reuse of 1. Because 3G, 4G is working at the frequency reuse of 1, I love the title of this, RF waste graph. Because all you need is a scanner. You don't need a handset to determine what the RF conditions are. And this contractor, a consultant actually, basically shared with me this graph to show where you have single sectors, where you don't have other sectors within 5 dB of that first one, you oftentimes get very high SINAR values when you have a single sector, whether it's at neg 60, neg 65, or neg 70, all the way up to, but as soon as you add a second sector within 5 dB, or you find a second sector within 5 dB of the first, you can dramatically see how quickly the SINAR values drop by the addition of a second sector trying to cover the same area. Now this is not unlike a conversation in a room. As long as there's one person talking, it's generally pretty easy to understand what's being said. But as soon as you start adding another presenter that's talking near the same audio level, you're going to have a harder time otherwise hearing and understanding them. The same thing applies when you're looking at the stars up at the sky and you have light. Again, back to that sound and light analogy. If I want to see all the stars in the sky, what am I going to do? I'm going to choose a day when the moon isn't out, and obviously I'm going to wait until night to otherwise, see as many of those stars as possible. Well, oftentimes in LTE technologies with modulations of 64 QAM, and oh, by the way, brace yourself, but 256 QAM is actually being explored by some of the network equipment manufacturers. It's going to get even more crowded. So understanding how to not waste your RF is going to be very key to seeing all that. Conductive susceptibility. This is a clear example, and these are actually screenshots taken from DAS system at Lucas Oil Stadium. And we were showing off our CellAdvisor many years ago, obviously, when the Super Bowl was there, and showing the visibility they had off their base stations. And in that case, or when we were showing them, the modulation quality was wonderful. It looked perfect. But the individual, as we were presenting it, and he was getting really excited, he basically finally asked me, can I look at the signal on the output of the DAS system? Well, the first question I had is it a neutral host? He says, yeah, but he says the building's not occupied. I can put in test points, do whatever I need. And sure enough, as we proceeded to go out to some of the remote radios and looked at that same signal, there was clearly degradation through the conducted RF that was passing through this DAS system. And I oftentimes like to use the analogy on a DAS system. It only has 2 primary roles. One is to wherever you place those antennas is that it shouldn't interfere with itself or the macro site. They shouldn't be competing with each other for that space. But the second purpose of a DAS system is to maintain signal quality from point A out to point B, and the same signals that come in from point B, that they maintain that signal quality back to point A. And in this case, you can clearly see that was not always the case. DAS systems can degrade the signal quality. In this case, as far as LTE overview, understand this. And again, we're going to talk a little about that 64 QAM. 64 QAM is the holy grail. If I can have my handset in a part of the coverage that otherwise has clear pilot dominance with minimal multipath power, again, references to types of interference, I can oftentimes achieve 64 QAM, provided I have a high-quality signal coming out of my base station. So as that reference signal comes down to the handset's going to use that reference signal to determine the channel quality. They have a CQI value all the way from 0 up to 15 that will otherwise try to help guide the scheduler on choosing the most appropriate modulation scheme to try to get right the first time. meaning LTE is one of those few technologies which is actually preemptive. It tries to establish what is the condition of the RF link, and let's try to send out the information one time so that we don't have to retransmit the same information twice. So this is part of that interference of understanding what type of service am I going to get based on the CQI values. But here are some interference rules to live by, meaning that if you've already gone through and determined it's not self-inflicted, and you are going to go out into the world to find that external source of interference, first things first, if the receiver can't see it, it is an interference, meaning that you have a lot of wireless technologies deployed in the 700 megahertz band. Don't know if you realize it yet or not, but much of the cable TV is also 700 megahertz. It just so happens it should be on a piece of coax cable. But you'll oftentimes drive into a residential area, guarantee you'll find lots of evidence where cable TV 75 ohm coax has been left open. But if that signal can't make it back to the receiver, it's not interference yet. Second point, always use a passband filter for the uplink. One of the greatest analogies I've ever heard is that if you go out to look at uplink interference and you're not using a bandpass filter, it's kind of like going out in the daytime looking for stars when the sun is out. If you have a transmitter adjacent to you as far as spectrum, it's going to make it very difficult, if not impossible, to find uplink interference. So that second rule is extremely important. Gain is important. Gain can come from a variety of things. The antenna itself will extremely, and we have slides that otherwise conveys this, this gain increases your efficiency in finding interference further away. DANL, displayed average noise level, is important. This gets back to that noise figure test equipment, and there's actually a specification published for every spectrum analyzer manufacturer where they'll give you specific settings of the spectrum analyzer and what is the displayed average noise level, meaning how many dB is it above Boltzmann's constant with those settings. And last is the calculate path loss, and we have more slides that will go into each one of these more in depth. But the calculating path loss is getting kind of back to that, if the receiver can't see it, it is interference. If you haven't done some very quick path loss calculations, you need to do that in order to determine if, in fact, that isn't the source before you start knocking on somebody's door and saying that they're creating a problem for you. It may not, in fact, be their source that's causing the problem. So, rule one, let's go ahead and expand on that. Does the receiver see it? External interference should be validated at the receiver if at all possible, so that you know what to look for and what not to look for. Interference is everywhere, so you could spend many hours fixing things that don't cause problems with your base station receiver, and I love these two examples. Example one, cable TV in an empty lot? Surely not. And Roy is actually the person that shared with me the story, that they had a customer they called on, that they knew it was cable TV, they'd plugged into the receiver, they saw the proverbial cable TV signature, and they're looking in front of the site, and there's a residential area just beyond. They proceed to drive the residential area, found lots of examples of cable TV interference within that residential area. But Roy was very quick to point out, and he has lots of experience in doing these path loss calculations, that based on where they were standing and understanding the gain of their antenna, that ultimately the distance from the base station could not have been the, source of what was causing that interference to that sector. Eventually they kept coming back to that empty lot and realized that, yes, in fact, there was a very strong cable TV presence, and they decided to go ahead and walk that empty lot, and sure enough, it kept getting stronger, and they eventually found that there was actually a 75 ohm coax cable that had been slightly buried by an excavator after they demolished some properties right in front of that cell site. So in fact, the cable TV was in an empty lot, something you wouldn't otherwise expect. The next example, this is on Lake Erie, and on a hot summer day, there was a lakeside amusement, a sector that was pointing at this amusement park would oftentimes experience very high noise floors on hot summer days. Well, after many, many months and finding or realizing it wasn't coming from the amusement park itself, because those path loss calculations, they eventually came to realize it was actually a sailboat that had been struck by lightning. It damaged most of the electronics and the electrical devices on the boat, the insurance company came through and replaced most everything that was otherwise no longer working, except for one item, the tower-mounted amplifier. So it means that every hot summer day that this guy would take his boat out and he fired up his radio and had that tower-mounted amplifier, it started spewing noise that otherwise caused interference to that sector until he got far enough away from that lake shore to otherwise no longer see it. So there's no end to the potential sources of interference. But does the receiver see it is really the first rule of what you need to understand and know what it is you're looking for. Now, in terms of efficiency, the first rule, there's 3 rules to testability: access, visibility, and controlling the device under test. Access is one of the biggest challenges that you're probably going to experience in your professional career, because what happens is if somebody hasn't provided test points at key points of demarcation, you oftentimes have to intrude and turn down service to otherwise create that test point, to find that visibility that you're looking for. So that third part, controlling device under test, that goes back to that OCNS AILG. But whether it be on the site with an RF connector, I actually have great admiration for Alcatel-Lucent, now part of Nokia Siemens, where they actually provided both transmit as well as receive test points on the TRDU. In the case of Ericsson's base stations, initial LTE base stations, the only thing they provided was uplink RF test points after the bandpass filters. Some I have great admiration for came up with, no, I need to have, and oftentimes I carry with me, low loss pass-through couplers that allow me to leave that antenna in service while I'm otherwise monitoring and looking at transmit quality off that 40 dB on test point. If that RF happens to be on a piece of fiber, in most installations, the fiber runs directly between the radio head down to the baseband unit. What I admire most is if you have a coupler that otherwise gives you that test point without having to interrupt the service to your customer. But if either way, you need that point of access. Here's that rule 2, using a bandpass filter for the uplink. Analyzers will create false signals when overloaded. Again, back to that dynamic range. If you overload the instrument and you get into that nonlinear aspects of the equipment, it will produce false signals. But one of the best ways, and we have a slide that describes this a little bit better, the best way to determine if a signal on the screen is real or not real is to actually use the built-in attenuators and markers to determine whether or not that level changes as you increase or change the internal attenuation. But filters are the best way to prevent most overload situations and not chasing signals which are not actually present in the environment, because you can get that result from a spectrum analyzer. You can also see degradation in signal quality when you're doing signal analysis on our instrument if you've in fact overdriven our instrument and you've not used not only a 40 dB down test point, but oftentimes added about 25 or 30 dB of internal attenuation when looking at your transmit signal quality. The other thing is, and one of the reasons why I use a mag mount antenna in this display, many of the veteran engineers that I have encountered that have been doing interference hunting, they will generally tell you that they no longer start with a directional antenna. Now, the exception to that is oftentimes if they can find a point, high point of elevation, meaning top of the building or top of the hill, and now there could be a long ways away from the source, but because they have an unobstructed view, that directional antenna having a high gain is a huge benefit. But if you start out with a directional antenna in and amongst buildings, you can oftentimes find yourself falsely accusing a building of being a source when in fact it's just a reflection off the front of it. So many people who are hunting down interference oftentimes always start out with a mag mount antenna on top of the roof and will try to identify exactly where they're at with that mag mount antenna, and they'll try to return to that same point with a directional antenna. But that's how they do the quickest and the most efficient way of finding interference is actually using a mag mount antenna and driving a very broad grid. And if you're in a building and you walk a building very quickly looking for where is it the strongest, as soon as you identify it, don't waste time there. Go to the floor above it, floor below it, and walk again a grid pattern and see, did it get stronger? Are you getting warmer? Are you getting colder? But please, do yourself a favor. I actually did an exercise with some of our TAC, our support individuals doing a training a couple weeks ago, and they were spending a lot of time with their direction antenna trying to figure out where it was. And what I really wanted to tell them, you need to step a little quicker because you're kind of serving as a distraction in this room, and you really are off by 1 floor because I'd actually placed the interference source on the floor below, but they were wasting a lot of time with the direction antenna trying to find it when in fact it was in the floor below them. They knew what part of the building it was strong, but they needed to proceed to either the floor above them or the floor below to see if it got stronger as they moved between floors. So here's that overloading analyzer. You may recognize this display. When you boot two carriers together in a nonlinear device, this is where you start seeing intermod. 3rd, 5th, 7th, 9th, 11th intermod products happen anytime you beat two frequencies together in a nonlinear circuit. So if you have in fact reached the area of nonlinearity on your test instrument, that's where your test instrument can start producing false signals when you overload it. And they display them right along together with the external signals. So if you want to validate this, if it's an external signal, when the internal attenuation is enabled, the spectrum analyzer will compensate automatically for the levels, displaying external signals at the same level. So for example, if you got an external signal at minus 50 dBm, it will stay at minus 50 dBm when the attenuation is added. If you're looking at an internally generated signal and you start adjusting your internal attenuation and it no longer remains at minus 50 dBm, you pretty much know immediately that this is being created within the instrument. It's not actually external to the equipment. Now, the other thing I actually thought of that I probably wanted to share with you, another huge advantage to using this mag-mount antenna, one of the options that we sell is a little stick antenna that you can put right on top of our instrument. And trust me, I use those, but my preference is I want the mag-mount antenna on a cable so that I can move the antenna out away from my instrument. Our instrument and every other manufacturer's RF test set will have some type of radiated emissions. By being able to move the antenna away from these electronic sources, you can oftentimes see, when you say external RF, but in fact it's being generated locally by whatever power supply, laptop, or vehicle that you may be in. So by being able to move the antenna and be able to see those correlating changes, you can oftentimes isolate that, yes, you may have a radiated emissions that's showing up on your spectrum analyzer, but is in fact not affecting your base station, only your display. Back to that rule 3, gain is important. What happens with path loss is that in free space, each 6 dB of gain doubles the distance from which you can see the interferer. So when you use that high gain band-specific antennas and low loss cables and you use your preamp, you can more effectively increase the range of where you can otherwise see interference if in fact it's an external interferer. So as you look through these example of 100 meters at 700 megahertz, there's 69 dB of loss. At 200 meters, the path loss is 75 dB. That's 6 dB of difference. So clearly you can see the correlation that if I can get 6 dB more of gain, you doubled the amount of area that you can otherwise detect where that Daniel is important. This is back to kind of your control your environment and know exactly what's going on with your spectrum analyzer. So when you use narrow resolution bandwidth settings, you can push that noise floor down. And again, every 6 dB doubles your sight distance and will generally reduce your drive time by a factor of 4 because the amount of area is, when you say, 4 times larger. You can also use fast analyzers that have FFT sweep settings. Our instrument, if you go to the sweep button on the numeric keypad, you will find there's normal, which is using swept-tuned methodology for doing spectrum analysis, or you can do fast, which is FFT, fast Fourier transforms, which greatly increases the speed of your sweep, which means you can continue to lower your resolution bandwidth to try to expose things more and more. Now this last point here, this is a huge pet peeve of mine, And even on this display, it kind of touches a nerve for me, because as I look at the spectrogram display, spectrogram is one of the single best displays to use for interference hunting. But as I look at this, I see two colors. I see green and I see blue. And although the interference in this case is actually quite obvious, because these little blips that you're seeing in the middle is not characteristic of an LTE signal. But what I'm getting to is by setting the reference level here at the bottom and pushing the peak power on the display towards the top, and then using the scale per division to have, a full red to deep blue display, this is like using a telescope, a microscope, a pair of binoculars, a magnifying glass. It serves to magnify the spectrum where details become more obvious. And also, in terms of dano and displayed, that display takes on a whole new characteristic where you can start seeing problems that weren't previously visible. But understanding how to use your equipment and what type of levels it typically shows under good conditions, in fact, I recommend investing time looking at good spectrum so that you otherwise understand what bad looks like. Now here's that key, and it comes back to that empty lot example we used. Rule 5, use path loss estimates. Path loss can help determine if the interference is impacting the site. Don't chase signals the BTS doesn't see. Back to Rule 1. Understand the noise level of your receiver. That noise power based upon settings of the preamp, attenuation, and resolution bandwidth. So we want to estimate the interferer's transmit power. Estimate the interferer's power at the BTS. Use a path loss table to make those estimates, meaning that you can pretty much, as you see a power at a base station as an interferer, you can pretty much determine by, drawing a line out from that site at what power levels would you otherwise expect to find or potentially find that interferer. So with that information at hand, you can then go through some calculations. I've seen a variety of equations. I tend to like this one, where D is the distance of the receiver from the transmitter in kilometers, and F is the signal in frequency in megahertz. And here you can see that at 751 megahertz, approximately 57.5 dB, basically 90 dB, that's a path loss 1 kilometer. At 1 meter, at minus 60 dB, that's a path loss about 30 dB path loss. At 100 meters, it goes up to 70 dB path loss. So you can start to see that 6 dB difference between 100 meters, 200 meters, 200 meters to 400 kilometers. So understanding the path loss, again, if you have 6 dB of extra gain, you can effectively double the visible area, in greatly increasing your interference hunting efficiency. But now let's show a simplified example of path loss. Here we actually provide a table with the distances in meters vertically, and then across the columns we have the various frequencies, 700 megahertz, 850 megahertz, because at each one of these parts of the spectrum you get different path loss, similar to a drum or a flute. Low frequencies tend to go further, meaning that your path loss values are lower than what you see at higher frequencies. You have a higher path loss as you get into higher frequencies. In this case, the LTE's channel is impacted by an interferer at minus 18 dBm or higher. Therefore, at BTS above 128, we added a 10 dB fudge factor, we're basically looking for anything that's within 10 dB of that neg 118 dBm, because that is, in fact, our, when I say, Boltzmann constant starting point. So we're going to look for anything that's above neg 128 dBm. We're going to basically try to investigate. So here are the frequencies at 1900 megahertz back at this baseband unit. The distance to interfere, in this case, 30 meters from our test instrument, where the distance to the base station is 500 meters, based upon where we see this potential source of interference versus where we know the base station is at. Since we know the BTS antenna gain to be 18, and 100 kilohertz resolution bandwidth that gives a power measure of neg 110, let's start with estimating the power at the BTS. So the measured power at the BTS, neg 110, plus that's what we're seeing actually measured on the instrument, neg 110 dBm on our instrument. So we basically say, okay, we went back, 30 meters, that's a path loss of plus 68, so it basically puts our source at a minus 42. Well, if we think about our source being at minus 42, could that be the potential source affecting our base station? Well, at 500 meters away approximately, we basically figure out that that's a 92 dB path loss from our table, right here, down here, underneath the 19 megahertz column. So at the antenna, it's at a minus 34 dBm. But as soon as we see a plus 18 for our antenna gain on the top of the tower, that means that, yes, that signal can be an interferer at a neg 116 dBm. It's obviously greater than neg 128 dBm, so it should be considered as a very likely source of interference to that base station. So this type of a table, understanding path loss, understanding your starting point and your reference points, both for your base station as well as your instrument based on the settings, are the key ingredients to locating and confirming whether or not these are actually sources of interference. So on the practical side, antenna gain at 10 dB is significant. Don't go a mile out if you only see that interferer on one sector. Now, on the antenna on top of the car is, again, oftentimes the best starting point. One of the ideal sweep times as you're lowering your resolution bandwidth, or if you're choosing between swept tune versus FFT for your sweep, is ideally I like to see at least 3 updates per second on that sweep time. So here are some of the settings which are key to a spectrum analyzer. Having 3 traces, a clear light trace, a min-hold trace, a max-hold trace. Turning on your preamp, especially for those weak signals. Setting your reference level in your dB per division to get that magnification. And last but not least is oftentimes turning on a peak detector can help you find those intermittent interferers that may otherwise get hidden through averaging and RMS settings. Next is a pre-selected bandpass filter to help with dynamic range. The bottom line is persistence and patience when hunting. Whether you're a fisherman, hunter, or someone hunting down interference, you need a strategy, you need to be persistent, you need to be patient, but more importantly, you need to understand the capability of your equipment. Whether it be test equipment, fishing rods, or rifles, you need to understand where do you use them and how do you use them. So in summary, much of the interference is at, meaning you're self-inflicted, or very close to the site. It can be a potential low-quality components, poor plumbing, again, back to the RF cable connector, poor hygiene, not tight and or damaged, or the fiber, same issue, poor hygiene and or damage. Grounding, antenna placements, not aware of surroundings, triangles versus squares. RF planning still using 2G coverage patterns that were never optimized for 3G, 4G coverage. Trust me, I've heard enough people say that they're still using antennas from 15 years ago that were originally put in place for GSM and may not have even gotten down tilted when they otherwise started deploying 3G, 4G technology. So if they weren't down tilted and they're still spewing out to a adjacent site that has the same frequency, this can be a problem. Low power emitters. Low power emitters close to the site is very close to the site. Only look for what is affecting the receivers. Don't look for something caused by overdriving the instrument. Don't call a tower climber unless you can consistently replicate the problem, meaning that you know how this problem manifests itself, and if it's something that's self-inflicted, you should be able to use your own transmitter to recreate the problem so that when the tower crew gets there, you can clearly see where they're able to help replicate that problem by tapping and torquing, or that you can clearly see that the problem has been fixed as they tighten or replace components. Can you control the transmitter output? That's really part of that replicating the problem. Be methodical, persistent, patient when isolating the problem, and bottom line, avoid more problems in the process. Control your setup, meaning don't try to think that you've in fact found a problem when in fact the problem is in fact your setup. So be very confident and also be very careful. Don't be too quick to start disconnecting RF connectors because you could be in fact adding more problems instead of actually isolating where the real problem is at. I'd also like to provide you one challenge. It's actually the same challenge I give to everybody that I give a training or presentation to, and that is if you really want to get good at something, the best way to do that is to teach somebody else. And what I mean by that is one of the best ways to determine your own strengths and weaknesses, as well as the strengths and weaknesses of your team, is to use your communication to teach them anything that you learn. And you'll come to realize that the basics are by far the most important aspect of anything you do. But again, I give you a challenge that anything you learn, teach somebody else, and it makes you that much better. So once again, thank you very much for attending. If you do have other topics that you would like us to address and bring up as part of these webinars, please reach out to Fabio or any one of us and let us know that this is an area of interest and you think it would be of value not only to yourself but to others within your organization or the customers that you serve. So please keep us in mind when you're having problems or trying to find or isolate those problems, and we'll do our best to make the best of your situation.